Take a completely rigid, sealed metal container full of a gas and begin to apply extreme heat to it. As thermal energy transfers into that closed system, the gas molecules inside absorb it and accelerate. Because the container walls will not yield, those molecules slam into the metal with increasing kinetic force, causing the internal pressure to spike rapidly. If you keep adding heat to this closed system, the rigid container will eventually reach its structural limit and violently rupture. So, how does a physical system safely absorb massive amounts of thermal energy without building up a dangerous level of pressure? To solve this, you have to completely change the boundaries. Instead of a rigid lid, imagine a heavy, movable metal piston resting directly on top of the gas inside a cylinder. When you apply intense heat to this new setup, watch the pressure dial. Despite the energy entering the system, the needle holds perfectly steady. In thermodynamics, this specific scenario creates what is called an isobaric process. The prefix iso means the same, and baric refers to pressure. It describes a sequence of events where the pressure of a system is strictly constant. But the fire is still pumping energy into the gas. If that energy isn't showing up as increased pressure on the gauge, it has to be transforming into a different kind of physical action. Watch the apparatus. As the gas heats up, it expands, pushing that heavy piston and the weight of the atmosphere resting on it upward. When a system exerts a force to move an object over a distance, it performs mechanical work. The gas is actively doing work on its surroundings. This equation calculates that physical effort. P stands for pressure, which remains constant, anchoring the calculation. The part in parentheses measures the physical space, the difference between the starting volume and the final expanded volume of the gas. Performing this physical work is the first major destination for the incoming heat energy. That volume expansion triggers a parallel consequence, tracked by completing the right side of the equation. Mu represents the amount of gas, and R is a universal constant. Because both are fixed, temperature, or T, becomes the true variable. This creates a strict mathematical requirement. As the volume expands to lift the weight, the gas temperature must climb alongside it to maintain balance. A rising temperature dictates a rising internal energy. At the microscopic level, the gas molecules are darting around and vibrating with increased kinetic energy. The heat from the fire is doing double duty. It isn't just lifting a weight, it's altering the internal thermal state of the gas itself. We can see this entire dynamic clearly by looking at how the energy flows through the system. Look at this diagram. We start with a concentrated stream of thermal energy entering the bottom of the cylinder. The moment that energy enters, it divides into two distinct paths. One fraction flows straight upward to move the piston. This represents the specific energy dedicated to external mechanical work. The second fraction is absorbed by the molecules themselves, driving up the system's internal energy and its temperature. In an isobaric process, every joule of input heat is perpetually divided between moving the physical boundaries and heating the interior. Because the system expands freely to accommodate the heat, the pressure on the walls never intensifies. Volume, temperature, and internal energy all shift to protect that singular, unmoving anchor of constant pressure.